more practice with Lewis structures, this is going to be different than the previous molecule in that it's an anion and there is a charge that has to be dealt with. So how do we account for that charge? So same rules. 1, count the valence electrons. Looking at the periodic table, carbon has 4, oxygen has 6, and there are 3 of them. Now, the -2 charge means that, well, the particle that is negatively charged that you've learned about is an electron. So the anion has 2 additional electrons. 2 minus, negative charge, 2 additional electrons. If it were positively charged, it would have 1 less. Cations have fewer electrons than protons. Anions have more electrons than protons. So the 2 minus charge means that you have to add 2 electrons, valence electrons. 4 plus 18 is 22. There are 24 valence electrons. So our Lewis structure has to match, has to have 24 valence electrons in it. 2, carbon's less electronegative than oxygen, plus there's 1 of them. It will be our central atom. And now 3, give each atom an octet. I'm going to start with the oxygens. They're more electronegative than carbon. I'm going to count, or recount, the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have too many electrons in my structure. What does this mean? Okay, I have 26. There are only supposed to be 24. But this method clues me into 26 minus 24. Again, that's math's not hard. There's 2 extra. Which means that there is the presence of a double bond. If I had 4 extra, that would mean I would either have 2 double bonds or a triple bond. Okay? But for every 2 extra electrons, that means you have to draw a double bond or a triple bond. Okay? Or excuse me, a double bond or a pi bond to be technical. But a pi bond, you'll learn about those more specifically in the next chapter. But for now, 2 extra, you have to draw another bond. So the notation to do that is I'm going to take and symbolize what I've circled there, that is where I want to draw that additional bond. Okay. Now you may ask, why didn't I draw the bond here or here? The answer is I could have. I could have drawn it in either of those places. All the carbon-oxygen bonds are equivalent. But for now, that's where I would like to draw it. Clean this up a little. Okay. So now it's important that what I circled here, notice that I took away both lone pairs of electrons, and I drew a bond, a new bond, between the carbon and the oxygen. Okay, you do that process for every pi bond, or double bond, or triple bond that you would draw. But we recount. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That matches our original count. So that is a Lewis structure for carbonate. Now this double bond, I could have drawn it here, I could have drawn it there. Those all would have been equivalent. And those are called resonance structures, when you have multiple choices for where you put that double bond. So now, lastly, where does that -2 charge come from? Well, I have to introduce formal charge. It's a formal charge. What is it equal to? It's equal to the number of valence electrons for the element in question. Let's just, as we go along, let's just say we're talking about oxygen. Oxygen has 6 valence electrons. Its group number is 6A, minus the number of bonds let's just say we're talking about this oxygen atom. Sorry about that. It has one bond. One bond. Minus the number of lone pair electrons. Which this has 2, 4, 6 lone pair electrons. Okay, not lone pairs, but lone pair electrons. So minus 6. So the formal charge for that oxygen, 6 minus 1 minus 6 is minus 1. And you can see that this oxygen is minus 1 because it's in the same shape, same scenario. One bond, 6 lone pair electrons. This oxygen, 6 valence electrons minus 2 bonds, 2 sticks, minus 4 electrons and lone pairs. It's a formal charge of 0. It's a carbon atom. It's 4 valence electrons. It's in group 4. It has 4 bonds around it. It has no lone pairs. Its formal charge is 0 as well. So, using the formal charge calculation will give you an idea. It's a bookkeeping device to help you rationalize where the negative charges are. When you learn more about resonance, at least you'll learn that that charge is spread out over the whole molecule. But at least on this structure, on this snapshot, that is how you would calculate where the formal charges are. So using formal charges to make a decision about which structure is best. So what you see here are 2 possible structures for formaldehyde. Now, if you check how many valence electrons you have for, or should have, carbons in group 4, hydrogens in group 1, there's 2 of them, and oxygens in group 6. So you have 12 valence electrons should be in each structure. If we count 2, 4, 6, 8, 10, 12, 12 in this structure, 2, 4, 6, 8, 10, 12. There are 12 in that structure. So they're both sound that way. Does each atom have an octet? Carbon, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. They have octets. Hydrogen, just a reminder, it's in the first period in the periodic table. It can have a duet, a maximum of 2 electrons. So 2, 2. Hydrogen can only form 1 bond. So this structure obeys the octet rule and the duet rule. So duet is fine for each of these hydrogens. This carbon, 2, 4, 6, 8. Octet, 2, 4, 6, 8. Octet. So everything has an octet rule. So to break the tie, or figure out which structure is better, we use formal charge. They were introduced in a previous play posit, or earlier in the play posit. But the shortcut way of how you remember this is how you calculate it. So FC, formal charge, is equal to the group number, the number of valence electrons, minus the number of bonds, minus the number of dots, or electrons. So if we look at carbon, it's in group 4. It's 3 bonds in this structure. 1, 2, 3. And there are 2 dots, 2 electrons around it. 1 lone pair. So a -1 formal charge. Oxygen, group 6. 3 bonds, 2 electrons around it, 1 lone pair. It has a +1 charge. Let's look at the second structure. Carbon's group 4. Has 4 bonds around it. There's no lone pairs. That formal charge is 0. This oxygen is a group 6. It has 2 bonds, 2 sticks, and 4 electrons. Its formal charge is 0. So the rule is minimum or minimal formal charges are best. So between the two, the better structure is this one for formaldehyde. Another couple things to notice is oxygen's more electronegative than carbon. So oxygen would do a better job of stabilizing a negative charge than carbon. And here, we've got a positive formal charge on oxygen and a negative formal charge on carbon. The opposite of what would be energetically favorable given electronegativity values. But again, formal charge, minimal formal charges are better for a structure.